So let's check out an example of using our inverse trigonometric function integral method. And a lot of times what we have to do is we have to use a little bit of creative substitution to make this work. And here's this example right here. We see that we have the antiderivative of dx of e to the 2x minus 1. Now, what we should note right here, first of all, that this looks kind of similar to actually this situation, because if we, for our arcsecant right there, and I'll explain why, in our arcsecant, we might note that we have dx over the square root of something squared minus 1, and we certainly do have that right here. We might notice that we have e to the x, and we can rewrite that as e to the x squared minus 1. And that would almost fit this situation, except that we have this little problem right here with missing, I don't know, how do we get this constant in there? Well, let's take a quick note that if we were to right now replace u for e to the x, then what should du be? Well, du should be e to the x dx. And we're missing an e to the x in the numerator as well, which kind of indicates what the trick is right here. We need to rewrite this one more time. And we're going to rewrite it by multiplying the numerator and denominator by the quantity e to the x. Why? Well, let's take a look at what happens. We've got e to the x in the numerator and e to the x in the denominator. Of course, e to the x over e to the x is the same thing as 1, so we're not changing the quantity there. And we're going to have e to the x squared minus 1 under our root. And so now we can see definitely, oh, well, we've got du right here in the numerator, right? That's a nice thing. And of course, we have e to the x, our u, in the denominator right there. So that's actually a really beneficial thing for us as well. So let's, that's supposed to be a little exclamation point because I like this. All right, so let's make the replacement. What are we going to do? We're going to get du in the numerator. In our denominator, we're going to get eu, replacing e to the x, in the square root of u squared minus 1. And, well, sure enough, yeah, that is this model right here. In this case, instead of a, our constant a squared is equal to 1, so of course that means a is equal to 1. We're just going to take the positive value of that constant. And what are we going to get? Well, we're going to get du divided by u square root of u squared minus 1 equaling 1 over 1 times the arcsecant of the absolute value of u plus a constant. We'd say u over a, but u over 1 is just u in this case. And so making our replacement right here, we're going to have the arcsecant. And we would say absolute value of e to the x, right? But, of course, you recognize that for all x, I'll justify this, for all x, in the set of real numbers, we recognize the fact that e to the x is always greater than 0, and so the absolute value is not really helpful here. And so we'll just rewrite this as the arcsecant of the function e to the x plus the constant. And that is our antiderivative here.